Hello everyone, I'm Kai. I'm a PhD student from the University of California, Merced. Today I'm going to talk about our recent work, ArchTM, Architecture-Aware High-Performance Transaction for Persistent Memory. This is a joint work between UC Merced and Lawrence Livermore National Laboratory. The first commercial persistent memory product is available. Compared to the hard drive and SSD, persistent memory has much better performance and also has better addressable access interface. Compared to DRAM, persistent memory has much larger capacity and non-volatility. On the left side figure of this slide shows a logical architectural layout of overturn-based machine. We have seen on each socket there are 6 DRAM DIMMs and 6 NVDIMMs. They are achieved directly to the memory bus. Processors can access persistent memory through load and store instructions. The data transfer size between the processor and the persistent memory is 64 bytes. The overturn internal transaction size is 256 bytes. The right side figure shows a performance characterization of the right performance of persistent memory and DRAM. First, we observe that the PM write bandwidth is significantly lower than DRAM, so reducing write traffic on persistent memory is critical. Second, we noticed that small random write on persistent memory perform worse than sequential write. This performance gap is caused by the 256 byte overturn internal granularity and write amplification. Third, we also noticed that random write on persistent memory have performance spikes at the right side that are a multiple of 256 bytes. Such performance is due to the effect of the write combining buffer. It buffers and combines 64 byte stores into a 256 byte internal store. Small concurrent writes to the contiguous memory space are more likely to be combined into one internal store than small write to random addresses. So, persistent memory microarchitecture characteristics such as internal buffer and data block size has a significant impact on the performance of persistent memory. In this work, we focus on transaction system designing for persistent memory. Failure atomic transaction is a critical mechanism for accessing and manipulating data on persistent memory. Existing persistent memory transaction systems are implemented into 2 major formats, login-based and copy-on-write-based. But both of them do not consider persistent memory characteristic of microarchitecture impact shown in the last slide. This slide shows how do these 2 types of transaction work. The login-based approach, including undo and logging, has 2 major issues. First, login-based transactions have to write and update twice on persistent memory, one to data and the other to the log record. This introduces actual write on persistent memory. Second, login-based approach performs in-place update, and the in-place update to the data could cause a concurrent random write because of transaction workload could update random persistent objects. Copy-on-write based approach avoids those problems, but it contains many metadata updates like memory allocation, deallocation, and remapping of the persistent object from the old copy to the new copy. Those metadata updates cause many small writes, which are very inefficient on persistent memory. Besides the issue of the existing transaction mechanisms, we also found that the allocation and deallocation algorithms used in the existing conventional memory control allocators are not efficient for transactions on persistent memory. First, the existing allocators usually use multiple free lists for each thread. Each free list supports allocation requests for specific sizes. Such size class-based memory allocation is used to reduce memory fragmentation. However, it allocates non-contiguous memory blocks to consecutive memory allocation requests if they are fulfilled by the multiple free list. Second, the existing allocator returns freed memory blocks to thread local free list directly. This procedure avoids the synchronization of managing a global free list, but may harm the locality of free memory blocks. Free memory blocks in a free list may be non-contiguous, so let's consecutive allocation requests get non-contiguous memory allocations. The above design issues probably reduce the possibility to leverage the commanding buffer hardware to coalesce writes inside the persistent memory. To solve the mismatch between the persistent memory architecture characteristics and the current persistent memory-based transaction design, we propose ArchTM. It is a transaction system customized for persistent memory architecture. According to the previous performance characterization, we have three major design goals: reduce write traffic on persistent memory, avoid small write on persistent memory, and encourage coalesable writes on persistent memory. For the first goal, ArchTM use a copy on write based approach, which can reduce the write traffic to persistent memory by avoiding double write of an update. To achieve the second goal, avoid small write on persistent memory, ArchTM minimizes the metadata modifications on persistent memory, but still provide cross consistency. On one hand, ArchTM keeps metadata including memory allocated metadata and persistent object mapping metadata on DRAM to avoid frequent data modifications on persistent memory. And ArchTM also uses an object lookup table on DRAM to fast locate the latest copy of a persistent object. On the other hand, to provide cross consistency, we introduce an annotation techniques. ArchTM annotates a transaction by adding a transaction ID into the transaction state variable. The embedded transaction ID is persisted immediately when the transaction state changes to star. ArchTM also annotates a persistent object by adding the persistent information such as ID, size, and transaction ID into the object header on persistent memory when an object is created. During the recovery from a crash, ArchTM uses the object ID and size to identify each persistent object on persistent memory. Then ArchTM uses the annotated transaction ID to identify the most recent copy of a persistent object, recycle the inactive copies, and discard uncommitted modifications. To achieve the third design goal, encourage coalesable write on persistent memory, ArchTM ensures that consecutive allocation requests to get contiguous memory blocks but minimize the memory fragmentation. First, contiguous memory allocation. ArchTM customizes the allocation and the allocation for transactional workload on persistent memory to maximize the possibility of a sequential write. Small allocations are the main focus of this optimization because sequential write benefits small object more than large object. In ArchTM, there are two data paths for persistent object allocation and deallocation. A regular data path for large object allocation and deallocations, and this data path is similar to the existing allocators. And the ArchTM also has a locality-aware data path for small object allocation and deallocations, and it is its optimization is based on a design of a single free list and the global recycling procedure. Because the single free list design may introduce the memory fragmentation, ArchTM uses a lightweight online memory differentiation techniques that detect memory usage by regions and reduce fragmentation on persistent memory. This slide shows an overview of locality-aware data paths in the continuous memory allocation and online memory fragmentation. For locality-aware data paths, a single free list is used in ArchTM for allocating of objects of different sizes To maximize the concurrency, ArchTM assigns each thread a dedicated portion from the global free list. When a thread tries to allocate a persistent object, ArchTM searches through the thread's private portion of the global free list to locate the first memory block larger than the requested size. When a thread deallocates a persistent object, the deallocated persistent object is added to the thread's private deallocation list. In the background, the garbage collection manager thread periodically collects freed memory blocks from the thread to the global recycle list. The global recycle list is sorted based on the memory address of the memory blocks. There is another background thread, which is the defragmentation manager thread. The defragmentation manager thread monitors the fragmentation ratio of each memory region in the global recycle list. Once the defragmentation manager finds an unutilized memory region, it will create a mock write transaction to aggregate persistent objects in underutilized regions and migrate them to a newly allocated memory region. If ArchTM cannot find free memory blocks from the global free list, ArchTM will use the memory blocks from the global recycle list to refill the global free list. To recover a program enforced by ArchTM after the crash, there are two steps. First, detect the uncommitted transaction. It is implemented by checking the state of each transaction state variable on persistent memory. ArchTM will collect the transaction IDs of the uncommitted transactions. Second step is rebuild the object lookup table. In this step, ArchTM creates a new object lookup table on DRAM and loads the object information to the new table. ArchTM will discard object copies in uncommitted transactions and reclaim their memory space. Meanwhile, ArchTM only keeps the latest copy by compiling the transaction ID annotated in the object copies. ArchTM also contains other optimization techniques such as scalable object refreshing, non-blocking rate. I will not introduce them in this talk due to the time limit. Please find more details in our paper. Now let's see some evaluation result. We use a real persistent memory architecture, which is Intel Optane DC persistent memory platform for evaluation. We run TPC-C and TATP benchmark on PMDK. We compare ArchTM with full state-of-the-art persistent memory transaction systems. This slide shows the throughput comparison among different persistent memory transaction systems on TATP and TPC-C. Overall, ArchTM significantly output other four state-of-the-art transaction systems. To conclude my talk, in this work, we pinpoint performance problems in common transaction implementation on real persistent memory hardware. We also demonstrate the importance of considering persistent memory architectural characteristics for transaction performance. We present ArchTM, which is an architecture-aware persistent memory transaction system. It is customized for real persistent memory hardware by avoid small write and encourage coalescable write. ArchTM demonstrates better performance than state-of-the-art transaction systems in the evaluation. Thank you.